for Vodcast 24, which is the second and final Vodcast for Chapter 8. We'll cover sections 8.41 and 8.42, plus also section 8.6. And in these sections, we are going to be talking about laminar, turbulent, and intermediate or transitional flow. And we're going to be using something in your textbook called the Moody Chart. So it's very important that you make sure that you have your textbook or an electronic copy of your textbook with you while we have this lecture, because otherwise using the Moody Chart is not going to make a lot of sense, because I'm going to be referring to it directly throughout this lecture. So having said that, let's get started with section 8.4.1. When we talk about a fully developed laminar flow, what we're talking about is, as we described last time, those situations where if you put a little dye streak into a fluid regime, that the dye streak will not blur and it will not look squiggly. It will just exhibit a laminar flow pattern, very literally, that the dye will just maintain its location as it flows through, and it won't blend in with other elements of the fluid. We've found that in the fully developed laminar flow region, that the friction factor, or the description of how friction affects flow, is just equal to the constant 64 divided by the Reynolds number. And it's actually independent of roughness and pipe diameter. So this is a very important fact. If the friction factor is not a function of epsilon over delta, it's only the case for laminar flow. So when you get into transitional flow, and definitely when you're in fully developed turbulent flow, the roughness of the pipe and the diameter of the pipe become very important characteristics upon which the friction factor depends. So the ratio E, or epsilon over D, is referred to as the relative roughness, and as you can see, it is going to be dimensionless. In other words, the roughness, or the pipe roughness, or the height of those little bumps in the pipe will be measured in dimensions of length, as will diameter. So when you divide those two out, you get a dimensionless characteristic. Now, if you have an epsilon over delta ratio of greater than 0.1, this is a huge roughness, and that is a type of a pipe where the roughness or the size of the blips in the pipe wall become a dominant factor. And what happens when we have these very, very large roughnesses, this is the case in like corrugated pipe, or sometimes, like in the old days, they used to take trees and hollow them out, and they would actually flow water through these hollowed out trees. It's had huge roughness factors. What that means for us is that we have an extremely rough pipe where really the friction of that pipe and the characteristics of the pipe pretty much dominates the flow regime. If E, or epsilon, is approximately equal to 0, and then F is not equal to 0, it's still not equal to 0 because we still have a no slip condition. In other words, even if the pipe were perfectly hydraulically smooth, which is what the name is of a pipe that has no epsilon, the friction factor is not equal to 0 because we still have the viscous forces of the fluid adhering to the surface of the pipe as the fluid moves through the pipe. So even a hydraulically smooth pipe does not have a 0 friction factor. Now, the way that we analyze this relationship, where we have some sort of a friction factor, and it may or may not be a function of epsilon over delta, and it is a function, or they're all functions of each other. These are not independent, except in certain regions, which we'll discuss. We need to have a chart that will correlate all three of these. And that chart is called the Moody Chart. And as I said, in your textbook, that is on page 477. Now, I'm going to put it up. I think it may be easier for you to see it if I put it up electronically, but I want to be able to point. When I have it up on the computer screen, all I can do is show you the page from your textbook. But the way that the Moody chart works is, you'll notice, first of all, this is a logarithmic scale, right? We have 10 to the third, 10 to the fourth, 10 to the fifth, equally spaced. So that means each one of those is a log cycle, or a power of 10. And the bottom shows us the Reynolds number, which of course is rho v d over mu. Now, for low Reynolds numbers, we know that that corresponds to laminar flow. High Reynolds numbers corresponds to turbulent flow. And in between, we have transitional flow. Now, on the left-hand side, we have the friction factor, which we're going to talk about how to use that in just a moment. And on the right-hand side, we have the relative roughness, epsilon over delta. Now, these epsilon over delta, or excuse me, epsilon over d, diameter. These relative roughness factors are for new clean pipes. As pipes get older, they scale up, and they get pitted, and so the roughness becomes larger than you would expect. So we are talking about new clean pipes. Now, if you look over here on this scale, what you can see about the friction factor, first of all, it's dimensionless. Relative roughness is dimensionless. Reynolds number is dimensionless. So all three of these factors, even though they can be independent or not independent, depending on what range you're in, they're all dimensionless. So as long as, it doesn't matter what set of units you use, if you're in the SI system, if you're in the US customary system, as long as you make sure that you are always dividing the same length by the same length and having consistent units with your Reynolds number, your friction factor will come out as a dimensionless characteristic that is dependent just upon those ratios, and it can be used for any set of units. Now, one thing that's interesting, the way that you use the Moody chart is, if you have a Reynolds number and you have calculated an E over D, you go into the chart along the bottom at whatever your Reynolds number is, and you move up to the line that corresponds to the relative roughness factor. When you hit that line, then you go over to the left and you can read the friction factor. Now, one of the things that you should notice is that over here, and over here for sure, and then somewhere in here, but from here to here, the relative roughness doesn't matter at all. In other words, the Reynolds number comes up to here, we read a friction factor. Well, that is in the region of laminar flow. In laminar flow, friction factor is not a function of relative roughness. It's just a function of the Reynolds number. And in fact, the friction factor is equal to 64 divided by the Reynolds number for laminar flow. Okay. So we've already said that, but you can see that on the chart, that these lines do not matter. All right, what you also see is that the relationship, how much epsilon over delta, how much the relative roughness matters, depends on where you are in terms of the flow regime, in terms of where you are with the Reynolds number. So at extremely high Reynolds number, if you reduce the Reynolds number from, say, 8 times 10 to the 7th down to 2 times 10 to the 7th, the effect of the roughness factor, relative roughness, doesn't matter at all. You're going to have the same friction factor. However, when you get into these transitional Reynolds numbers, like if you go from 10 to the 6th to 10 to the 5th, you can see that the friction factors are significantly different for the same Reynolds number based on the relative roughness of the pipes. So when you use the Moody chart, this is a great empirical tool for solving a lot of different kinds of problems, but it's just good to understand where all of these numbers come from. So dimensionless, 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 logarithmic scale, friction factor only a function of Reynolds number for laminar flow, strong function of relative roughness as well as Reynolds number for transitional flow, and less, it's still a function of relative roughness, but changing the Reynolds number doesn't significantly change the Reynolds number, excuse me, the friction factor based on different, or based on the same value of relative roughness, I guess would be the way to put it. Let me say this again. Friction factor is a function of Reynolds number for fully developed turbulent flow or wholly turbulent flow, and yet the change in relative roughness for very high turbulent flow patterns doesn't affect the friction factor as much as it does for turbulent flow. All right, so what we're getting at here, this is just a little drawing that I made showing the teeth. This would be the epsilon, or the relative height of that pipe roughness, and the diameter, kind of showing why we have this relationship. And the one thing to remember when we are dealing with flow regimes is that we are not just dealing with a pipe, and we're not just dealing with a fluid. The combination of the fluid and the pipe makes up the system, and all of those factors are important to what's actually going to happen. Now, there are a couple of equations that are very important in terms of using the friction factor to describe a value of head loss. And this first equation can be used for either horizontal or inclined pipes, and it is referred to as the Darcy-Weisbach equation. Now, Darcy was a very famous civil engineer from France. His first name was Henri, and Darcy developed a lot of the radial flow equations that are currently used in the petroleum industry. So you'll see his name come up again and again, especially if you're a chemical or petroleum engineer. But you can see that the head loss that we experience, and this is we can think about what the units are in just a minute, but the friction factor, which is dimensionless, times L over D, which is also dimensionless, times V squared over 2G. All right, V squared is going to be in length squared per second squared, and G is in length per second squared. Okay, so second squared cancels out, length cancels length, and we're left with dimensions of length for head loss. All right, now do you remember when we were working with the Darcy equation, we had forms, when we were working with the Bernoulli equation, we had forms of the Bernoulli equation where we talked about energy in terms of feet of fluid. And this is essentially the same thing. We're talking about how many feet of fluid we lose for our head due to the friction of the pipe, of a particular pipe and fluid moving through that pipe. So we go ahead and we just talk about this. If there's no friction factor, that would mean that you have a totally inviscid fluid, and that the no-slip condition would not exist. Right? So sometimes you use different thicknesses, or different smoothnesses or roughnesses of pipe to control your flow. If you have, for example, water in an irrigation system that is on too steep of a grade and you want to slow it down, you can use a rougher pipe. So you can use concrete pipe rather than PVC pipe, still keep maintaining a flow full condition or whatever conditions you want to use, and yet you can lose some of that head, some of that energy because of the roughness of the pipe. Or if you have too shallow of a grade, in other words, if your pipe is not moving downhill as fast as you would like to maintain a fluid behavior, a particular velocity or flow rate, you can use a smoother pipe like PVC pipe in order to maintain a faster flow, or to pass more flow, or to lose less head. All right, now we're talking right now, H sub L, we're talking about major losses. In other words, we're talking about the losses that result, the energy losses specifically, that result from fluid moving through a pipe. Now there are other losses which are all sort of collectively called minor losses, and they are due to fittings and directional changes, entrances and exits. So anytime that you have a coupling or a splitter or a T, anything that changes anything about the flow of the fluid, you're going to lose energy based on that change. So we refer to a loss coefficient as KL, and we can say that the head loss from those minor losses is going to be whatever KL is for that particular fitting or directional change or whatever, over times V squared over 2G. This is written kind of strangely. 2G. Let's put it that way. All right. So if we have a total loss coefficient, in other words, if KL is 1, that means that our velocity is going to go to 0 and our fluid will stagnate at that point. All right. Now, there are times where you can use these ideas of losing some energy to your advantage. Sometimes you want to lose energy. And what I've drawn here, this is a diagram, more or less, of a dam with a topper put on it. And this is similar to the Buffalo Bill Dam back in the 1980s. Let's see, Buffalo Bill Dam was built originally in, I think, before 1910, about. And it was expanded, or the size was increased, so it was renovated, I guess you would say, in approximately 1990. And there were two reasons for the renovation. The main reason is that a whole bunch of silt had built up at the bottom of the dam, and so there wasn't as much storage capacity as there had been originally. The Buffalo Bill Dam was primarily constructed for irrigation and farming, although it has other valid uses as well. But it was originally constructed for farming, and so the capacity behind the dam was integral to its function. And so as the silt built up, less water was able to build up behind the dam or to accumulate behind the dam. And so we had to increase the size of the dam. So there was solid layers of the dam where the height of the dam was raised. But then on top, there was this pillar structure. If you go out there, you'll see what this looks like. But basically what this pillar structure does is that if a dam is overtopped, in other words, if the spillways and the controls on the dam are not sufficient to prevent water from going over the top of the dam, the force of the water going over the top of the dam will actually pull the concrete of the dam off, or can under terrible circumstances, and that can create a dam failure. So in other words, the concrete will start to pull away here, and then it will pull away further and further down until the dam will actually fail. If you have a break here, what actually happens is there's a fluid phenomena where the water will move away from this and constrict itself into what's called a vena contracta. And so there's less water actually touching the side of the dam, or these pillars, with the way that it breaks up like this. So instead of just having a clean bar of water going across the top, if you think about that, just a clean, uninterrupted flow, you have several interrupted flows. And what that allows, the vena contracta allows the dam, while it's being overtopped, to not have the same force, the same magnitude of force of water going over it. And when that happens, we're quite a bit actually better off in terms of pieces of the concrete starting to roll up with the water and being driven off. All right, so when we talk about all of these things, when we talk about losses and we talk about friction factors and we talk about relative roughness, what we're really getting at is we want to be able to say, in a particular system, how much water is going to move through, how fast is it going to move, and what's it going to do to the inside of my pipes, which is a little bit more of a finesse question that we're not going to be able to answer quite yet. But we are going to be able to talk about how to meter water, either in terms of flow rate or in terms of velocity. So when we talk about section 8.6, we talk about how much water is actually coming out of a real system. Well, you know that we've previously calculated Q as being equal to a velocity perpendicular to an area. And while that's true, we lose the actual, I guess I should put this over here. This is actually a Q ideal. Depending on the type of structure that the water flows through, we lose some percentage of that. And these are empirically determined, and a few of them are discussed in your textbook, beginning on page 513. If you look in your textbook, beginning on page 513, you'll see that there are coefficients that are assigned to different types of flow regimes. So for example, at the bottom of this page, right here, I can point with my cursor, we have that Q is equal to C of an orifice. An orifice, you just have this discharge coefficient, which is C sub O, equal to some sort of a Q ideal. And so these are calculated differently depending on the type of meter that you're going through, the type of restriction that you have. So, for an orifice, we use C sub O, or C for orifice. And we can see what the pipe flow geometry looks like. And we can look at what an orifice meter looks like. So you can take a look at these. We're not going to go into them in great detail. Just that if you see water going through an orifice, you know that you need to determine what that coefficient needs to look like. Similarly for a nozzle tends to be something that is smaller in area at the end of the flow, or at some point in the flow in the beginning. So in other words, it's like a garden hose that you squirt water out of. It's a nozzle. So you have a different type of a coefficient, which is called C sub n. So in all of these different cases, whether it's, and then you also talk about a venturi, which is something that is just it's something that squeezes something down in the middle, flares at the beginning, and flares at the end. So all of these just have different types of coefficients that we use to determine what the actual Q is going to look like compared to that ideal Q that we calculate, which is V times A. All right, so we're not going to go into this in great detail. Suffice it to know that those ideas exist and where to find them if you are given something like this. All right, so now we're going to look at problem, I'm going to come back over here to the document cam, and we're going to look at problem 8-94. This is in your textbook on page 529, and this is a fairly representative problem of the types of problems that you'll be working in your homework. So problem, I'm sorry, I said 529. I mean to say it's on page 529. It's problem 894. So if we take a look at the podium PC, we can see that over here, let's go ahead and zoom in on a little bit so you can see it a little bit better. All right, so what we have is, this is not the picture that goes along with it. We'll have to draw our own picture. We have water that's being moved from a large closed tank in which the air pressure is at 20 psi into a large open tank through 200 feet of smooth pipe at a rate of 3 cubic feet per second. The fluid level in the open tank is 150 feet below that of the closed tank. Determine the required diameter of the pipe. Neglect minor losses. All right, so what that's telling us is we're going to neglect minor losses, orifices, venturis, and so forth, and also the entrance and exit effects. We're not going to be neglecting the loss that's associated with the fluid moving through 2,000 feet of pipe. So we could calculate a Q over A. We have a different pressure, right? This is 20 psi. This is open to the atmosphere, so it's P gauge of 0. We have 2,000 feet of pipe, so we have some sort of an HL based on that. And we have a Q. And we also have a height difference. We're told that they're 150 feet different. So the water's flowing down due to pressure and due to gravity. So what we need to do as we work through this problem is set it up, take into account what the head loss looks like, and calculate what sort of a diameter we're going to need for this flow to occur. All right, so the first thing I do is I write out the form of the Bernoulli equation that's sort of, I always refer to it as ginned up, where we include the head losses, and if we had a pump or a turbine, or a pump, for example, we would also include head gains. Now we also know that all of our head losses are just going to be the major losses from that length of pipe. So I have my pressure head initially, my position head initially, my velocity head initially, my pressure head at 2, my Z, or my head at 2, and my velocity head at 2, plus my friction factor. All right, so when we get in and out, when we get into the tank up above and the tank below, the velocity is 0. I know that Z1 minus Z2 is 150. I also know that I have 20 pounds in the first tank and 0 pounds in the second tank because it's open to the atmosphere. So I can calculate my velocity based on my Q ideal, or my Q of 3 cubic feet per second, area of the pipe, and I can calculate a velocity that is a function of the diameter. It's obviously not a linear function, but basically this is the number I need to find. Okay, so I need to know, in order to get, I have this velocity, it's going to be a function of the diameter, what's going to get me the flow rate that I need. Okay, now this would be a simple question if we didn't have head losses, but in this case we don't. So then I go back to Bernoulli and I plug in my pressure term and my delta Z term, and then I have my friction factor. So I have the friction factor, which I know, F times L over D times V squared over 2G. And I have V as a function of D, and I have D over here as well. So I have D in a couple of different places, but I can manipulate this equation, and I also have to remember the 20 psi. If I'm going to change it into, this is per square inch, I need to go per square foot, so I need to do my conversion to 144. And I get an equation then, after I get done with this, that says the diameter of the pipe is going to be equal to 1.18 times the friction factor to the 1/5 power, which is also 1 over 5 is just 0.2. Now, there's an interesting thing that happens with these types of problems. They often become trial and error or iterative solutions. Because if you look at the Moody chart, the nature is that we have a friction factor and we have a Reynolds number. And if they're both functions of the diameter, we have to find what's going to make this problem work. So what I've done, I've set up a trial and error solution to this problem using Excel. And I would recommend that you do this as well. These are the easiest ways to do these types of problems. All right, so what I've done here is I've taken that equation that I developed with my pen and pencil, that 1.18 times the friction factor raised to the 1/5 or the 0.2 power is equal to the diameter. I've also calculated my Reynolds number as a function of mu, rho, velocity, and diameter. So they're both functions of diameter, aren't they? So I have Reynolds number is equal to this value divided by d, and the friction factor raised to the 0.2 times 1.18 is equal to d. Now, if you recall the Moody chart, which I'll bring up on the screen here, let me flip over to the document cam so you don't have to watch the scrolling of the screen. But back here on page 477 of your textbook, we have a version of the Moody chart which shows you that we have the Reynolds number. Don't really have a roughness in this particular case, and we have a friction factor, and we have to find something. We have to find numbers, a number for D that's going to make the Reynolds number and the friction factor correspond to each other. In other words, that will solve both of those equations, and that is the reason for the trial and error solution. So what I've done is, on my spreadsheet, I choose a value of F, I calculate D, and then based on that D, I calculate the Reynolds number. Now, I do need to make sure that my epsilon over delta value is equal to 0, which it is. It becomes a much more complicated problem if it's not. But basically what I do then is I go into the chart and I find my value of F. Now I chose, the number I used in my calculations is 0.01, and I calculated 0.012. Since 0.01 is not equal to 0.012, I then know that this is not a good number. So I increase my value of F to 0.02, go through the same process, calculate an F of 0.013. Once again, I compare the two. 0.02, which is my assumed F, is not equal to my chart value of 0.013, so I have to increase it. I go to 0.013 again, and I check, and I'm getting closer, right? When I use a value of F of 0.013, run through my calculations, my F value in the chart is 0.0125. And then you can also see that I just try, since it's close, I try 0.0125, go through the same calculation, and then I have a value of F of 0.0125, so I know that I have found the correct value of friction factor of 0.0125. So then I can take that value and I can calculate at that value of F that my diameter of my pipe is 0.491 feet. I got that right here, right? I didn't have to recalculate it. It's just the value that was calculated based on my chosen friction factor. So I know that I need a pipe that has a diameter of 0.491 feet in order to deliver that flow rate. So I'll put that down here. And we get, therefore, from the trial and error solution, a D equals 0.491 feet will deliver the required flow rate. All right, and if you would like, I will put a copy of my spreadsheet. It's very simple. I'll put a copy of that Excel file up on the web page so that you have an example to follow when you are looking at the, let's see if I put it up already, when you're looking at your Moodle page. So you'll have an idea of how to go about that. So let's take a look down here. For chapter 8, yep, there it is, okay? Trial and error solution to problem for 8.94. So you can pull this up and you can see what my formulas look like and so forth. All right, the last thing I'd like to do is to work problem 8-108 from your textbook. And 8-108 is on page 530 in your textbook. So if you look at 530 and you look at problem 8-108, it's right over here. Right. And we get a 50 millimeter diameter nozzle meter is installed at the end of an 80 millimeter diameter pipe through which air flows. A manometer measures pressure attached to the static pressure tap just upstream from the nozzle indicates a pressure of 7.3 millimeters of water. Okay, first of all, you would expect it to be small because we're talking about air and the flow of air. The other thing, though, that you should clue into is the fact that we're talking about a nozzle. So what we're really doing is we want to calculate an ideal Q, an ideal flow rate, and then we need to multiply it by the coefficient that we have for nozzle. And so here's a picture that I've drawn. We have air going in, 80 millimeter in diameter, static pressure tube that tells me that the gauge pressure of the air flowing is 7.3 millimeters of water. We have a smaller diameter here on the other side of the nozzle of 50 millimeters, and since it's open to the atmosphere, we have a pressure of 0. All right, well, we're given our area, pi d squared over 4, so we can calculate that directly. We know that the nozzle CN looks like this. We can go to our textbook, section 8.6, find out our equation, which says that Q is equal to the C for the nozzle, times AN times this square root 2 times delta P divided by rho times 1 minus B to the 4th. All right, we have a value of B that is given in the textbook. B is calculated by taking the diameter of the small end of the nozzle divided by the diameter of the large end of the nozzle, so it's 50 divided by 80, which comes out to be 0.625. So that is my beta variable that goes right here. So we know that this is pi d squared over 4. Calculate that. We have a P2 minus P1, and we can work through that, change it into some good units of pascals, Newton per meter squared, and we get that P1 minus P2 is 71.5. So now we're ready to go back into the equation. We have Q is equal to C times the area times this stuff, and we get a value that looks like this. All right, we also see that Q is going to be a function of the coefficient of the nozzle. So we have a velocity, and we have a Reynolds number, and we have a C sub n that we can calculate. And once again, this is going to be a trial and error solution. So you need to run through the equations with the values that you calculate and come up with a trial and error solution. And for this particular problem, Q turns out to be 0.0223 cubic meters per second. So in this particular section, a lot of the problems will turn out to be trial and error, because those are the problems that are going to kind of mimic real life, in the sense that we always get problems that are trial and error solutions, or often. All right, well, that's it for Chapter 8. So we'll do 2 more vodcasts on Chapter 9, and then that's it for the entire course. It'll also be, after you do 7, 8, and 9, you'll be ready for your 4th and final exam prior to the final exam itself, and then you'll be done with the course. So when you finish Chapter 8, get your homework done, turn it in to me, and then come back for Vodcast 25 and 26 for Chapter 9. Thanks, and we'll talk to you later.